Welcome to this explainer. Okay, I want you to look around you right now. Chances are you're sitting in the middle of this invisible, constantly pulsating digital infrastructure. I mean, we live in a world where our physical reality is just seamlessly layered with this massive, interconnected network of machines, and they are quietly talking to one another all day, every day. It's an absolute marvel of modern technology, right? But it also hides a much darker, way more complex reality. So consider this for a second. What actually happens when your smart home betrays you? It's a pretty chilling thought, isn't it? We literally invite these everyday gadgets into our most private spaces, mostly just for the sake of convenience. But the second a cyber attack happens, those exact same devices, we're talking your smart thermostat, your fridge, your security cameras, they suddenly transform into a sprawling, active digital crime scene. Okay, let's dive into this. At its core, the Internet of Things, or IoT, is really just a massive web of interconnected devices. Think physical objects packed with unique identifiers and sensors that are constantly processing and sharing data in real time. And the sheer scale here is just, it's hard to even wrap your head around. It encompasses everything from that smartwatch sitting on your wrist right now, all the way up to massive industrial sensors monitoring the entire global supply chain. To make sense of this massive ecosystem, here's our roadmap for today. First, the connected world. Second, how devices talk. Third, the open doors. Fourth, digital detectives. And finally, the future of security. We're going to uncover exactly how this tech works by exploring how it breaks and how we investigate it. All right, let's jump straight into section 1, the connected world. Let's set the scene of our digital environment. Because the IoT network is literally everywhere, spanning huge domains like healthcare and agriculture, it comes with this monumental challenge, and that is data generation. These IoT systems are pumping out such an overwhelming amount of data that it can instantly bottleneck core networks. So to actually handle all of this, researchers introduced this incredible lossless compression method called Beyond Orion. By using some really advanced encoding strategies, this method successfully shrinks dataset sizes by up to 99%. I mean, that is a total game changer for taking the load off system hardware. Okay, moving on to section 2, how devices talk. Let's map out this digital floor plan so we know where all that massive amount of data actually lives. Now, what's really interesting about this slide is how we can trace the exact journey of a single piece of data. If we look at the 3-layer architecture here, it all kicks off at the perception layer. That's your physical stuff, the components and sensors actually collecting data out in the real world. From there, it travels up through the network layer, which handles all the connections and routing. And finally, it hits the application layer, which is what actually delivers those software-specific services directly to you, the user. But here's the thing. As IoT has exploded in scale, that architecture absolutely had to adapt. We're now seeing this huge shift toward cloud and fog-based architectures. Because honestly, instead of sending every single tiny piece of data all the way to some remote centralized server, these systems are now pushing that data processing right out to the edges of the network, exactly where those smart devices actually live. Think of it kind of like this. Cloud computing is essentially a federal headquarters. It's centralized, it has massive scalability, but it can suffer from high latency because that data has to travel a really long way. Fog computing, on the other hand, that's more like your local police precinct. It's totally decentralized, operating right there at the network edge. It processes data locally and super quickly, giving you low latency and near instantaneous responses, which obviously saves crucial time. Which brings us to section 3, the open doors. Because having this intricate digital floor plan is fantastic for efficiency, right? But it also leaves the door wide open for bad actors. The core problem we are up against is perfectly summed up by this quote right here. Most IoT devices are vulnerable to attacks due to a lack of standardized security measures. You see, because these devices are built to be cheap and built to be efficient, they almost always have really constrained memory and low-power CPUs. They simply do not have the computational muscle to run the heavy-duty security protocols needed to actually protect your data. And because of those constraints, man, the network faces a staggering volume of threats. We are talking everything from DDoS and man-in-the-middle attacks to side-channel intercepts and literal firmware manipulation. And in almost all of these cases, weak device authentication is the #1 entry point for unauthorized users. They just slip right through the cracks of these low-memory gadgets. Okay, moving to section 4, digital detectives. So, when a breach inevitably happens, how do we actually figure out what went wrong? Well, enter the fascinating world of IoT forensics. Investigators basically rely on this incredibly precise three-step forensic process. Step 1 is detection, and this is often done passively using frequency mapping to figure out exactly what devices are even present at the scene. Step 2 is localization, where they analyze the received signal strength to physically track down those compromised nodes. And finally, step 3 is recognition. This is where they actually collect the digital trace evidence, matching up things like MAC addresses and electromagnetic signatures to uniquely identify both the device and the manufacturer. But the real challenge here is that digital evidence in an IoT network is incredibly fragmented. So the crucial point is how researchers solve this using brilliant tools like the last of seen or loss algorithm. Instead of trying to analyze millions of scattered data points, loss literally zeroes in on the very last item found in communication. By shrinking the investigation zone down to a zero zone, it actively prevents a massive workload, isolating the exact evidence they need and saving tons of time. But let me ask you this. If a hacker breaches your smart home network right now, where's the evidence actually stored? Because these IoT devices usually don't have the memory to keep historical logs or even reliable timestamps, that evidence might not even be on the device itself. It could be floating in the fog layer, up in the cloud, or just fragmented across a dozen connected nodes. It really makes this academic problem of decentralized memory feel incredibly urgent, doesn't it? But don't worry, help is on the way. Section 5, the future of security. Let's take a look at the cutting-edge upgrades currently being researched and deployed. And this brilliantly illustrates the diverse toolkit we'll be relying on for the future of security. By integrating blockchain, we get these immutable ledgers that basically guarantee an unalterable chain of custody for digital evidence, meaning courts can actually trust it. Deep learning frameworks are stepping up to automatically track and categorize cyber attacks. And then you have these incredibly lightweight cryptographic systems like RAM-MEN authentication that actively secure communication sessions while cutting communication costs by up to 45%. Meaning they do the job without draining the device's super limited memory. Let's move to and see how this builds into active defense systems. Researchers are now developing adversarial security models using deep reinforcement learning algorithms, specifically things like dueling double deep Q networks, or D3QN. Now, I know that sounds like a mouthful, but what it means in plain English is that multi-agent AI systems are literally learning how to actively patrol your networks. They are out there optimizing defense resources to hunt down and stop complex intrusions in real time. It is essentially an AI security guard for your smart home. So, bringing this all together, we have mapped out the massive, layered architecture of our connected world. We've looked at the very real open-door vulnerabilities stemming from these low-power devices, and we've seen the advanced forensic techniques from frequency mapping all the way to AI network patrols that are currently fighting to safeguard our digital floor plans. The push toward robust authentication and edge processing is absolutely transforming how we protect our data. I want to leave you with one final, provocative thought today. As sensors become more and more deeply embedded into literally every aspect of our daily lives, and as our physical reality completely merges with these networks, is the sheer convenience of your smart devices actually worth the permanent, invisible digital footprints they leave behind? It is a serious question we are all going to have to weigh as we navigate this hyper-connected future. Thank you so much for tuning into this explainer. Keep questioning, keep learning, and I will see you next time.